In Chapter 9, the complete response of a circuit with the two energy storage elements. In this chapter, the title of this chapter is the complete The title of this chapter is the complete response of circuit with two energy store element. That means the energy store element is inductor or capacitor. So now in chapter 8 we are discussing about the circuit which has the one inductor or the one capacitor. In chapter 9 we discuss about the circuit with two different energy storage element, inductor or capacitor. That could be inductor is L and capacitor C in RCL circuit or RLL or RCC. They're almost, in the case, each case is a two energy store the element. For example, this is a voltage source, resistor, capacitor, inductor. This circuit consists of one resistor, one capacitor, one inductor. Or it consists of two different inducting case. For example, the voltage source here, resistor and resistor inductor, and the inductor in this case here. There are two different inductor, L1, L2. Or the voltage source, resistor, capacitor, and resistor and capacitor in this way here. There are two capacitor. This is the two energy store element. So all of these kind of the circuit has a two energy store element. So in chapter 8 we discuss about the voltage source, resistor, and capacitor. It has a one energy store element, C or L. In this circuit can be expressed with the first other differential equations. Why? Because there one capacitor has kind of the relationship between of current and voltage is the derivative. So this circuit contain only one capacitor. So the expression of the characteristic of this equation, this circuit, is the first order differential equation. But in this case, we have two different elements of the energy store element. In that case, because there are two differential relationship between current and voltage. So in the case of capacitor is I is C dt dV, and inductor is V is L dt di. So because this circuit contains two different differential equation, so when you describe the voltage and current in this circuit, there are two second order differential equation. So everything is same, but when you describe the characteristic of current and voltage in the circuit, the equation is second order differential equation when the circuit has two different energy store element. So that's only thing we need to focusing on. So to basically to solve the electric circuit with two different L or capacitor, we need to know how to solve the second order differential equation. You don't need to have a burden to describe it here, because we will very formalize the equation, and I will give you a lecture to describe how to solve formalize the second order differential equation. It's very simple, and we don't need to. You don't need to hesitate to approach to solve that. It's not difficult. It's very simple. Okay. So, to complete the responsive circuit with the two energy storage element, there is a second order circuit. We call that circuit is second order circuit. The second order circuit can be represented by the second order differential equation. The general form over here is d square xt to alpha dxt and omega 0 square xt equal to ft. So we call x is output of the circuit. There's our constant variable. It could be x. It could be a voltage of capacitor or the current of inductor. And y is the input of circuit. Oh, excuse me, this is not y, it's f. It's long. F is the input to the circuit. So this is the force values, for example, the voltage source or current source values. And when you derive the second order differential equation from the circuit, we make this form the variable. Then you call the alpha is the damping coefficient, and omega is the resonance frequency. So it's very complicated but very simple. At first, I will tell you how to solve the second order circuit. It's very similar to the chapter 8 when you solve the first order circuit, because this circuit is represented by equation, the differential equation. So at first, we need to know about the initial condition. So we have to focusing on how to get the initial condition. Then next step is simplify the circuit. So we have to focusing on what we wanted to do. So except of the variable we wanted to know, we can eliminate by the usable tools such as Thevenin equivalent circuit, Norton equivalent circuit, or the source transformation, and KCL, KVL, whatever it is. You can simplify circuit. Then they reprint the circuit by the second order differential equation. Because second order circuit consists of at least two different energy storage elements like capacitor or inductor. The characteristic equation to represent the circuit is the second order differential equation. Then what should we do? To get a complete response from the differential equation, we make a xt will be sum of x and t plus xft. xn is a natural response. xf is a first response. Here fx is not different compared to first order the differential equation. What is the fx when in the case of the first order differential equation? There is the same form of input. In this second order differential equation, fx also the same form of input. So based on the input, we can get a fx exactly. So this is not difficult, but the natural response is a little complicated because the characteristic of the equation in first order circuit, the solution of natural response is general form of x and k exponential minus or minus tau t. Well, in the case of second order differential equation, it will be a little bit complicated. So this will be burden to approach this the analysis electric circuit. But this is very important because the natural response contains the all characteristic of the electric circuit. This is very important. So when you design the filter or any other function to some specific things, you need to design the electric circuit. The characteristic of the electric circuit is depending on this electron response. So this is very complicated, but if you learn these whole things about natural response, then it's quite be simple. So you don't need to burden to study of natural response. Last, the X is XNT and plus XFT. As you know, XNT has some unknown constant. So to get it, what should we do? We should be using the initial conditions. So in here, so we can find out the net unknown variables of natural response. So this is the same way to solve the first order circuit. But the different thing is, that's it. Step 4, how to get the natural response. In the case of first order circuit, the natural response is very simple. That's it. But in the case of the second order differential equation, the natural response a little bit complicated, but you don't need to hesitate to study it. It could be simple if you study all things. So in chapter 2, we discuss about how to get the second order differential equation from the electric circuit. It's very simple. We have discussed about two methods: the direct method and the operator method. We will discuss later, but at first, direct method we discuss here. The first thing is to obtain the second order differential equation. At first, we should identify the variables x1 and x2. So generally, you need to figure out x and x2 would be a capacitor voltage or the inductor current. And write one first order differential equation based on the variable one of them. And it could be a function of x1 and x2. Then obtain the additional first order differential equation. But in this case, x2 can be a function of x1. And substitute this equation to the here. And because of first order, then it could be go in here. So the final equation will be second order differential equation. So I will give an example. Okay. At first, we'll have an example how to obtain second order differential equation from circuit. Okay, this example. This is the example circuit is like that. That's it. We'll define R and L and C, and you define this current is I, and define this voltage is V, and the source is IS here. So based on this electric circuit, we will find out the differential equation to describe the current and voltage characteristic of this circuit. First, step 1. Identify variables x1 and x2. So we define generally when you define these unknown variables, you should choose the current of inductor or the capacitor voltage of capacitor. So here we define the I here and V like that. Then step 2. So write one first order differential equation. I mean, based on the current I and V, we can make any first order equations. Well, you can use, maybe I think we can use here. This is node. I apply the KCL. Then, because this current is go up here, so plus IS, and because this voltage is the V, so this current will be V divided by R, but direction is out of the node here, so it could be minus. And I will be minus, and actually, what is this current over here? Because of characteristics of C and V, we know that V equal, I is equal to IC equals C dt dV. So there will be minus C dt dV will be 0. So we rewrite this equation IS equal V over R plus I plus C dt dV. We define this equation is A. This is the first other differential equation here. Then, but this, I mean, we have two different variables, I and V, but this first order differential equation consists of I and V. So we cannot derive one variables. To make a one variable differential equation, we make step 3. Additional first order differential equation. Generally, the first order differential equation can be written by describing the two variables I and V here. So you know the characteristic of L, what is that? V is L dTd I. Then that variable is same with that variable. So we know that V will be L dTd I here. This is another equation, B here. Then next, step 4. Substitute the B to A. So IS V over R plus I plus C dV, and the V adding the V is L dTd I. So rewrite this equation. IS will be V over R plus I plus C dTd L dTd I. So we rewrite here is V over R plus I plus constant, so LC dt squared d squared I. So we summarize this equation more simply. Then LC dt d squared I plus I plus V is 1 over R L dTd I equal IS. So you summarize here, multiply 1 over LC I'll use different color. 1 over LC, 1 over LC, then rewrite d square I plus, where's that? RC, 1 over RC, DDI plus RC, 1 over RC, I will be 1 over RC, I is. This is the general form of second order differential equation. The general form of U is d square x plus 2 alpha dtd x plus omega 0 square is ft. So here alpha is 1 over 2rc and omega 0 will be root 2 lc, 1 over root 2 lc. So this is the general form. Then this is the differential, second order differential equation to describe the characteristic of this electric circuit. This is the way how to obtain the second order, the differential equation from the circuit. You need some practice to drive here. I will give you very general form. This is the first general form of the RS parallel RLC. Next is example of the series RLC circuit. Here. So this circuit looks like plus minus and R L C here. Define this is the VS, this is R and L and C. At first, what should we do? We should define the variables we wanted to know. Generally, inductive circuit, when circuit contains the volt capacitor or inductor, then current of inductor can be written as a common variable we want to know, and the voltage is that things. So I and V we define here. Then we make one first order differential equation. How to get it? Because this is connected series, we can define here. Based on here, because this voltage is Ri, and here inductor, we define the VL is, define this is a VL is L dTd I, and you put the V here. So based on the loop, the KVL, you know that the VS, we define the minus VS, so minus VS and plus RI and plus VL and plus V equal 0. So RI plus VL is L dTdI plus V equal the VS. We define the first order differential equation with the voltage, current and voltage here. And next, we need to figure out the relationship between an I and V here. So we know this is I, so the characteristic over here is I will be C dTd V. Then we subtract this relation to the first order, the first equation. So we do that here. R replace C dTd I plus L dTd C dTd V plus V equal Vs. So at first I will use here LC dt square V plus RC. Oh, excuse me, this is not I, this is a V here, this long. dTd V plus V equal the Vs. So rewrite here, dt square, we multiply 1 over LC, 1 over LC, then it'll be square V plus R over L dt dv plus 1 over LC V equal 1 over LC Vs. So this is the general form of the differential, the second order, the differential equation. You know, we already know the general form over here. What is that? dt square, the square V plus 2 alpha dt dv plus omega omega 0 square, the V will be ft. So alpha will be 2L R over 2L, and omega 0 will be root 2 LC, 1 over root 2 LC, and ft will be 1 over LC, the Vs. This is a general form of the second order differential equation here. So as you see, it's not difficult, it's very simple. If you know the KCL and KVL, it's very simple, it's not difficult. I will give you another example. Example of two inductor circuit. Okay, this is the voltage source here, and there's an inductor and resistor here, and there will be inductor here. We define this is R, and that is L1, and this is L2, and this is the Vs. So here, first we should define the variable we want to know. So what can you do? We generally define the inductor current or capacitor voltage. Here there are two different inductors. So we have two second order differential equation. That means we need to know the two variables. So we define here, this is define I1, and define here, this is I2. Then we need to make a first order differential equation to describe the system here. The first, we can use it because of this current that we can note here. This is the VL1, and we define this current here, this voltage here. Then when you define the KCL, we know the KCL here. I1 is going here, and I2 is go out here. So this current will be plus I1. We define this IR minus IR minus I2 will be 0. Therefore, IR will be I1 minus I2. So that voltage over here is R I1 minus I2. So based on here, we can first add the differential equation based on here. Vs will be the same way. VL1 plus R I1 minus I2. Then VL1 will be L1 dTd I1. We put here. So Vs will be L1 dTd I1 plus R I1 minus R I2. We cannot solve this equation. Why? Because there are two variables in I1 and I2 we want to know. So we need one more things here. Then next thing is this voltage, this voltage is R and I minus I2. And based on this branch, we can get this voltage here because of inductors, the VL2 will be L2 dTd I2. So this voltage and this voltage is the same. So we got it. All I1 minus I2 will be same is L2 dTd I2 here. So I1 will be I2 plus L2 over R dTd I2. This is an additional, the first set of differential equation to describe the relationship between I1 and I2. And we substitute the value over here. So we rewrite here the Vs will be L1 dTd I1 is I2 plus L2 dTd I2 plus I2 plus L2 dTd I2 minus I2. We make a more simplify here. Here L1 dTd I2 plus L1 L2 over R dt square d square I2 plus RI2 plus L2 dTd I2 minus RI2. Then we make rearrange here L1 L2 dt square d square I2 plus here L1 and L2 here L1 plus L2 dTd I2, and you may think it is eliminated here, so there will be Vs. So we make simplify by multiply L1 L2 L1 L2, then dt square d square I2 and plus L1 L2 L1 plus L2 dt d I2 will be L1 L2 the Vs. So this is a general formula here. So compared to variables, you know dt square d square xt plus 12 power td xt plus omega 0 square xt will be ft here. So here alpha will be L1 plus L2 2 L1 L2 and omega 0 will be 0 and ft will be L1 L2 the Vs. This is a parameter to describe this second differential equation with the general coefficient here, alpha, omega 0 and ft here. So this is a way to describe the general equation. So we cover the example that here. Until here, I will introduce the direct method to obtain the second differential equation. Now, another method is operator method for obtaining the second differential equation. And this is the way to the derivative. It changes the s. You already know about the Laplace transformation. This is Laplace operator is the s here. So in the Laplace operation, the s means the differential. So it change the dTd will be s. Then the meaning of the differential equation. So to do here, the rule of the Laplace transformation, using the Laplace equation, you can transfer the differential equation to the arithmetic equations very simply. So when you use the Laplace, then the differential equation can be simply solved, very easy, simply solved. We will discuss about the next semester, the second theory, second. When you solve the differential equation, you can solve very easily using Laplace. But here, in this point, we will not do that. In the operator method, just using the symbol of S to make a simple second differential equation. That's it. Using the Laplace equation, Laplace transformation, we will solve the second order differential equation in next semester. But okay, the way to using the operator method, at first we should define the variable x1, x2 is the same, because we need to define the variables we have to get in. That is the inductor current or capacitor voltages. In the same way, you can write one differential equation based on the x1 and x2, the same things. And we obtain the additional differential equation in terms of x1, x2. Right? This is the same. Then use the Laplace operator. The differential is S and the integral is 1 over S. Then change with two equations with that variable x1 based on the S. Then last, we convert the S to the derivative variables, derivative operators. Then we can get the second order, the differential equation. I will give you an example over here. Same example we discussed before. Here plus minus and inductor and resistor and inductor here is L2, L1, this is R, and this is the Vs. Then we already discussed about how to get the variables. It is I1, this currently is I2. We should define the differential equation based on this I1 and I2. Then I can make our first differential equation. It's very simple. First thing is this voltage will be this voltage VR1 and this voltage VR. Because Vs will be same way VR1 plus VR. And VR1 will be L1 dTd I1, and VR is R I1 minus I2. So insert variable here. So Vs will be L1 dTd I1 plus R I1 minus I2 here. The second thing is we get the relation between over here. And this voltage also VL2 will be L2 dTd I2. So VR will be same with VL2. So VR was here. So second equation is this is L first R I1 minus I2 will be same with L2 dTd I2 here. So we write here L I2 minus I1 oh, excuse me, it's long. Okay, R1 minus R1 minus I2 will be L2 dTd I2 here. We define this equation in second. Until now, we are same result with the previous method. Then here we use operator. We use replace. Okay. dTd will be replaced by s operator, and integral dt can be 1 of s. So we right here is vs. Vs will be L1 and derivative over here. So L1 change. Okay, I will leave it right here. dTd I1 plus L I1 minus L I2 here. Then Vs will be L1, that will be changed with S, and I1 plus or I1 minus L I2 here. Then we can make more simplify. Vs is common is I1, so L1S plus R I1 minus L I2. The same way we can do it here. Then in the case of second, L I1 minus L I2 will be L2 dTd I2. In the same way, this operator can be replaced by S. So we can read right here, L I1 minus L I2 will be L2 S I2. So L I1 will be same in L2S plus R I2 here. So I1 will be same with 1 plus R L2S I2. Now what should we do? We should combine two equations here. So we combine this equation right here and rewrite equation Vs will be L1S plus R 1 plus R L2S I2 minus L I2 here. Then we can use 1, 2, 3, 4. So first thing is L1S plus L L1 L2 S square and plus R plus L2S I2 minus R I2. Then that will be eliminate each other. So L L1 L2 S square plus L1 plus L2S will be I2. So can be rewritten here. This is divided by L1 L2, and that will be, this is Vs, and multiplied by L1 L2 R. Then this equation can be written here as square I2 plus L1 L2 R L1 plus L2 S I2 equal L1 L2 the Vs here. Then what should we do here? We replace S will be dt d. So we rewrite here dt square d square I2 plus L1 L2 R L1 plus L2 dt d I2 equal L1 L2 R the Vs. So this is a same weight. This result here, you know, dt I2 square dt square I2 square L1 L2 R L1 plus L2 L1 L2 R L1 L2 L2 same weight, that variable is same. So two results is exactly the same. So this is a different way to gather the operator. I mean to gather the second order differential equation to describe the second order second. Next example is a different example. We have some variable here. We will do this using the method we describe here. So problem example 9 and 2 and 1. The problem is the find differential equation for the I2. That means later we will want to know the line 2 here. So okay. Example 9-1. Okay. A1, I2 looks like a mesh current, but in the viewpoint of here, the I1, actually, the I1 is this current over here, and I2 is this current here. So, but when you make a differential equation, you need to make variables want to know. Then we should choose what variable we want to know. Generally, inductor current and capacitor voltage, because there are two inductors. So we have to make. We need to know two variables: that this current over here and this current here. So this current is defined as I2. Why? This inductor contains only one for this loop. So I2 is all current, the flowing through the one held this inductor. So the inductor flowing through this inductor is I2. So then we can use I2. But in the case of I1, this current is not exactly I1, because I1 is a mesh current of this. I2 is this mesh current of this, but this inductor included in the both mesh, the first mesh and second mesh. So the current flowing through this inductor is I will be I1 minus I2. I'm sorry, this is not this I. I mean, this current we define this name of this is I. Looks like here. Then we need to make an equation. And at first, what should we do? we can use the KVL here. This is Vs. Then we know this voltage E, because the current is I1, so their voltage VR, and this voltage is a VL. So Vs will be same way, the VL plus the VL. Then VL will be, let's say 2I1, and VL will be the voltage difference here. That will be the, the VL is L dTd I. L is 1 Helly, 1, and dTd, actually I is function of I1 minus I2. So Vs will be VR 2I1 plus dTd I1 minus I2. Get right here. Then what are the second things? We need one more differential equation to get here. Then we know that VL is derivative here. In another way, VL is the voltage of here and here. This voltage is, current is I2, so L dTd I2. Inductance 1, so that will be dTd I2. And the 3 ohms, so this voltage is 3I2. Therefore, VL will be same with dTd I2 plus 3I2. So we make one more equation here. The VL is that variable, dTd I1 minus dTd I2 will be same with dTd I2 plus 3I2. So we can simplify here. dTd I1 will be 2 dTd I2 plus 3I2. So we have two differential equations, that one and that one. But I want to use the operator method. What is that? You can replace dTd equal to S. Then you can rewrite this equation. Vs will be 2I1 plus S I1 minus I2. So Vs will be S plus 2I1 minus S I2. And also we have same things, S I1 equal to 2 S I2 plus 3I2. So there will be 2S plus 3I2. Therefore, I1 will be 2 plus 3 divided by S I2 here. Then together, the second differential equation, we should combine the two differential equations here. So adding here, right way, then Vs will be S plus 2, then two plus 3S I2 minus S I2 here. Then Vs will be, how much is it? 2S and plus 3 and 4 plus 6 over S I2 minus SI2. So there will be S plus 7 plus 6 over S I2 here. Then what should we do? To get the general form of a second differential equation, we multiply S here. Then SVS will be S squared plus 7S plus 6I2. Then what should we do here? S will be dTd. Then dt square d square I2 plus 7 dtd I2 plus 6 I2 will be dtd vs. So this is a second differential equation of the I2. This is a way to get the current over here. So until now, we discussed about how to get the differential equation to describe the characteristic of the second order circuit. So what do we do is listen. We covered how to represent the circuit by second order differential equation. The reason the first step is the same with the first circuit, and second thing is the same with the first circuit. Then, in the case of second order differential equation, a second order circuit, we should figure out the second order the differential equation to describe the characteristic of second order circuit. We deal with how to second order differential equation. Then, based on that, next step is the same in here regarding the natural response and the forced response, and finally we need to know the unknown variable to get the complete the solution over here. So to do that, to get the variables when we using the initial condition of the first step. So today we discuss about how to get the second order differential equation from the circuit. So next we'll discuss about the natural response of the second response, the second order the differential equation, and first response is the same. Okay, but it looks like complicated to get a second order differential equation, but as you know, as you try here, in the second order circuit, the form is very fixed. Because the general form of the circuit is very fixed. So if you try the several type of circuit, and you can get the differential equation simply. So I recommend you to do together some exercise and try to solve the example of the problem. To get a complete the solution over here, you need to know what is the lateral response and the first response. This is a simple way. The first response is determined by the input. So the first response, the form, is the same with the input as we discussed in the first order the circuit. And lateral response is more complicated. There are many different cases to describe the second order differential equation. But this is very important because the characteristic of the circuit is represented by this natural response. So next chapters we will discuss about the natural response and what is different compared to the first order differential equations.